Progressive methods demand refractories that withstand heretofore unobtainable temperatures and volume of production. Permanente periclase has been synthesized through intensive research by Kaiser Chemicals Division. This periclase produces the finest refractories. During World War II, expanding Kaiser Industries needed improved refractories. Having a qualified research and engineering staff of long experience and their own proving grounds, they selected Natividad in the California Coast Range near Monterey Bay as a source of high magnesia lime. Here they built a mineral processing plant, a network of belts, crushers, and classifiers that finally beneficiates and activates the starting mineral in a number of great tubular rotary kilns. In spite of the 40,000 tons of cleaned mineral quarried each month to supply the plant, this mountain provides an inexhaustible resource of high purity minerals. This quarry yields high magnesia lime suited to a closely integrated plan of production. The essence of the plan? Careful selection of materials and rigid control of methods to produce highest quality refractories. My manufacture starts with obtaining the lime mineral. Careful fracturing of the quarry face causes the material to descend as it is dug away. But occasionally a large piece must be reduced by mud capping. A charge of dynamite stuck to the surface with wet clay shattered. Reducing a mountain to a usable form is the first step in separating the high magnesia lime from unuseful materials occurring in natural deposits. Monstrous electric shovels dig away at the broken rock, placing it in dump buggies for transportation. The mixture of mineral and waste is dumped into a large hopper from whose mouth the rock is slowly worked by the grizzly so that it is fed continuously into the maw of the primary crusher. Converging steel plates working against each other crush the rock into smaller pieces. This is the first phase of purification. Another unusual feature of this quarry is the discrete structure of the mineral. The jaws crush, the rock cracks along the weak veins of included impurities, and the residue crumbles from the chunks of pure magnesia lime. Everything falls from the crusher onto the endless belt that travels to the primary classifier. The screen mesh is designed to retain all of the pure mineral possible and to reject the more finely divided waste to the tailings pile. From the primary screen, the magnesia lime is carried down to the processing plant, where it is washed with high-pressure sprays to remove adhering waste. Every precaution is taken to deliver only the cleanest mineral of the quarry to the stockpile. The rock then takes a scenic railway ride up a 100-foot boom and plunges to the pile below. The stockpile is drawn upon from reclaiming tunnels beneath for around-the-clock operation of the rest of the plant. Conveyor belts carry the rock to the secondary crusher. Several sizes of rock are going through this cone crusher simultaneously. Large chunks from the stockpile are being reduced, with several intermediate sizes recirculated from the classifiers. These select materials small enough for industrial use and return larger pieces for recrushing. The rock will be recrushed and screened until it is reduced at least to the size of a boy's marble. Vibrating classifiers bounce the rock down their inclined screens, keeping on top the rock that is too large. Material passed by the screens is carried by belt to storage bins, from which are drawn the desired sizings for shipment by truck and rail to industrial users. However, most of the finished rock is stockpiled for further chemical treatment. Heating the high magnesia lime to 2,000 degrees in the rotary kilns changes the mineral chemically and activates it for further processing. This kiln treatment is called calcining. Calcining drives off carbon dioxide gas, leaving a very active caustic chemical. The process may be explained by a simple demonstration. A Bunsen burner, a retort, and a beaker of carbon dioxide indicator comprise our apparatus. The mineral is placed in the retort and heated. To illustrate the mineral crystal and what happens to it, in this model, the red sphere represents a magnesium atom. The orange, calcium, carbon atoms are black, and oxygen green. The first movements of the model represent activity at room temperature, which is slower than the mineral crystal that actually oscillates in the order of millions of vibrations per second. As heat is applied, the temperature rise causes more rapid movement. When the temperature reaches 1,300 degrees, the carbon dioxide group of the magnesium has gained enough momentum to break its bond and fly off. At 1,832 degrees, the calcium loses the remaining carbon dioxide group. The gas bubbling into the indicating solution forms a precipitate and establishes that carbon dioxide has been released during the heating process. Inside the kiln, the magnesia lime is fed at the far end 300 feet away and is slowly carried down the inclined tube by its rotary motion. Large suction fans draw air into this, the firing end, and pull the hot air over the entire course of the mineral, drying the rock as it first enters, then raising it to calcining temperature of 1,800 degrees. The material resulting from this process is a crumbly mixture of equal parts of magnesium oxide and calcium oxide, about half the weight of the starting mineral. When calcining is completed, the processed chemical is emptied into coolers, through which air is drawn into the kiln, cooling the discharge and preheating the air to aid high firing temperatures. The coolers discharge the chemical to a belt below. This chemical is now activated and ready to combine with other chemicals in the next step of my synthesis. Now the simplest of my refractory family, dead-burned dolomite, may be made. Increasing the kiln temperature to 2,900 degrees causes the calcined crystals to shrink to a dense granular mass. This action is aided by adding iron oxide. The iron oxide reacts with the lime and the mass sinters to a dense, hard, very refractory grain. This material is primarily used in repairing furnace bottoms. The processing plant gradually converting the mountain to a useful material turns out 16,000 tons of finished chemical products each month. And now we turn to the sea. The great Pacific Ocean is drawn upon to contribute in the next phase of my production. The activated chemical from the kilns is mixed with seawater to start the synthesis of an ideally constituted periclase. For centuries, mankind has relied upon nature to supply his needs quite directly. Today, however, it is possible through modern science to synthesize a material better suited to his needs than some materials afforded by nature. This is what Kaiser scientists have done. The ocean provides an inexhaustible supply of seawater. 500 million gallons a month are pumped through this pipe to the plant. Just 1 cubic mile of water will operate this plant for half a century. Purification begins as the raw seawater is discharged into the large tank. This water contains undesirable material, which is removed by the addition of a small amount of calcined chemical. The removal of these substances prevents contamination of the product during further processing. Vanes move around the tank bottom to keep the water agitated, ensuring thorough mixing of the active mineral while scraping the settled precipitate into the sludge discharge. Treated water rises to the top and overflows to the 2 parallel tanks where any solids carried over settle out before it enters the slurry mixer. Here, activated magnesia lime from the mountain is continuously mixed with purified seawater to form a slurry that is fed into the reactor tank. In this tank, the magnesium oxide and the calcium oxide of the lime react with components of seawater. Magnesium oxide hydrates directly with water to form milk of magnesia. Calcium oxide reacts with the magnesium salt present in seawater to form a calcium salt, thus liberating magnesium and oxygen together, which then hydrate. The slurry inflow is a suspension of granular activated magnesia lime. Booms, driven from the center of the tank, constantly stir the mixture. The grains react slowly with the seawater, forming hydrated magnesia. Fine grains react more rapidly than the coarser ones, which settle to the bottom, where they are drawn off and recirculated with fresh slurry. A portion of the settled sludge is diluted with seawater and then passes through a rake classifier. In this way, heavy, unreactive impurities are rejected, while light magnesia and still active lime are returned. Rigid control of the entire process is assisted by continuous sampling of the reaction. The desired milk of magnesia is held in suspension near the surface, where it gradually moves with the current until it overflows into a sluiceway. Close control permits only fully reacted chemical and dissolved substances to flow on to the thickeners and washing tanks. Fresh water for cleansing the hydrated magnesium product is purified in large tanks by treatment with calcined lime, as the seawater was. The purified fresh water enters the 4th purging tank and moves slowly through the 3rd, 2nd, and 1st tank, contrary to the movement of the magnesia. The magnesia suspension from the reactor settles to the bottom of the 1st tank, where it is withdrawn to the next tank, while the exhausted wash water and depleted seawater overflow, returning to the ocean. The magnesia passes through the succeeding tanks, remaining about a week in each one, while being scrubbed with 700,000 gallons of fresh water every day. The thickened magnesia from the last tank is concentrated by Oliver vacuum filters. A large drum revolving in a slurry tank draws the suspension onto a filter cloth that removes the water. The cake dries partially as the drum carries it to the scraper, where it is removed from the filter by a wire. This milk of magnesia is almost of pharmaceutical purity without further refining. The cake falls from the drum into a screw conveyor which feeds it into one of these giant kilns. The milk of magnesia is calcined just as the starting mineral was, except that water is given off in place of carbon dioxide. Control is indispensable. By instrument, by constant vigilance. Several types of magnesia grains are produced, each tailored for the specific use it is to be put. Exact calcining or sintering temperatures are maintained to assure certain qualities of the specified grain. Various sintering additives to the kill feed are measured to tenths of a percent to compound the prescribed nature of the product. As a result of ingenuity and strict surveillance, in this kill I am born, my components cast in infernal fires to meet with competence the roles for which I have been designed. A complete range of chemical magnesia products is shipped over 6,000 tons each month to users throughout the world. Most of this is perlite, a synthetic raw material made up of 93% or more crystalline magnesium oxide. Basic refractories consume the largest portion of perlite. For this use, the grains must be crushed, sized, and proportionately combined to produce the densest possible mass. At the refractory plant, all the various ingredients that are used in basic refractories are assembled, sorted, and stored for use. The principal ingredient is perlite. This is required in many sizes, termed aggregates, plus the fines, which are mixed with the aggregates to fill the spaces between them, as sand is mixed with rock in concrete to make it stronger. Some refractories require special ingredients, such as chromite. Chrome ore is imported by cargo loads from the Philippine Islands. As the plant, it is cleaned, crushed, sized, and stored to be compounded with the aggregates in certain bricks and mortars. An ingredient of all permanente bricks is one of the products from this furnace. 3 tremendous electrodes fuse iron and silica into ferrosilicon. Our main interest here is the dense cloud of vaporized silica produced by this furnace. This form of silica has no crystalline structure and is of exceedingly fine particle size. The particles are no larger than any found in common cigarette smoke. The vaporized material makes possible the formation of a heretofore unknown bonding structure for the periclase grains. Like a giant mortar and pestle, the Simpson mixer blends all ingredients for brick from a formula prescribed by laboratory test and industrial service. This method makes possible the best mixture for its intended use. 2 1 3/4 ton mullers spread the materials while alternating scrapers between each muller dose it, first outward, then inward, then outward. This action of spreading and gathering mixes thoroughly and rapidly. First, the aggregates, from the size of split peas to dust particles, may be added. Then the bonding substances, vaporized silica and powdered magnesium oxide, are proportionately added to the mixture. Water to moisten it to the right consistency for pressing is added next from spigots above the scrapers. This water contains dissolved cementing chemicals that give the bricks great strength until they are fired and the ceramic bond produced. After mixing for a few minutes, a slot in the mixer bottom opens, emptying the mix onto a conveyor belt to the brick press hoppers. Ramming mixtures for furnace bottoms are blended dry in a similar manner and carried to sacking hoppers. This hopper is feeding a brick press. This press is one of a battery that shapes and compresses the mix from the hopper into a structural building unit. The moistened mixture of aggregates, fines, bonds, and binding materials is compressed to any desired shape and size. Shape is determined by the die. and accuracy of size by the tolerances maintained. Each set of dies will press about 9,000 bricks before it is worn to the 64th of an inch tolerance permitted. Each press is capable of exerting 2 million pounds every stroke and of turning out 18,000 bricks a day. As the bricks come from the presses, they are relatively soft. The cement has not yet set. Curing is accomplished by placing them in a steam autoclave for a few hours. When they are withdrawn, the chemical bond cementing agent has set, making them strong for shipment and installation. Some bricks may be fired in a tunnel kiln to achieve the ceramic bond before installation and firing in the customer's furnace. Every brick is color-coded as soon as it has been completely processed. This distinctive coating identifies each brick accurately at a glance. Coming from the mountain and the sea, my elements have been extracted, purified, united, and combined with other selected ingredients to form me a refractory brick. Now I and my family are ready to go to work in industries wherever furnaces must tolerate high temperatures and basic chemical reactions. Every month, Kaiser produces thousands of tons of the highest quality permanente refractories. Bricks, unburned and burned, ramming mixes, cements and mortars are shipped to various industries. Among them are cement, open hearth steel, electric steel, glass, copper, not all furnace brick is of the basic type. For instance, the brick in this soaking pit, which keeps steel ingots hot for rolling, is a non-basic clay refractory. But where the specialized basic refractories are required, their inherent characteristics are paramount. The incredible heat of boiling steel is only one of the drastic treatments a basic refractory must withstand. Water, solid at 32 degrees, turns to steam at 212. Steel has a ruddy color at 1,000, melts at 2,800, but does not boil until it reaches 3,200 degrees. This terrific heat is reached in open hearth furnaces, which are built with basic materials. These refractories must also have strength to support loads, measured in hundreds of tons. In the past, unfired bricks have been able to withstand a reasonable amount of wear and tear in handling, but sometimes failed under loads when fired in service. Testing various chemical bonds in brick mixes by hydraulic press has enabled Kaiser engineers to greatly strengthen some of those previously employed. Accurate addition of a chemical solution to the bricks forms an exceptionally strong chemical bond. Magnesium chloride, magnesium oxide, and water form an interlaced network of crystals, such as you see forming under the microscope, magnified thousands of times. This network embraces all of the ingredients compressed into the brick and gives it tremendous strength, as cement does in the setting of concrete. When the brick is fired, the chemical bond is gradually replaced as the firing heat produces the ceramic bond. The microscope reveals the amorphous appearance of the ununited, unfired ceramic bond material. When the brick is fired, the components react under high temperatures to form a closely knit crystalline structure. Because the bond components are of exceedingly fine particle size, they recrystallize directly into the desired unmeltable ceramic bond. No intermediate liquid substance is formed. To demonstrate what this means in practical terms, 2 bricks are placed in a test furnace, each supporting an equal weight, equivalent to that found in actual service. The brick on the left, made with average bonding materials, collapses at about 2800 degrees because liquids form in its structure. The brick on the right, containing smoke-sized bonding particles, holds up well beyond 3000 degrees, as liquids do not form in this brick. The finely divided bonding materials in one of these 2 pellets demonstrate that such bonding materials render a newly made brick at its greatest density. The pellets, pressed from mixes under the same pressure to the same size, are placed in a test furnace and heated to normal firing temperatures. The pellet on the left contains the superior bonding mixture. Watch the coarser bond mixture shrink the pellet on the right. The 2 inside pellets are the fired ones compared with similar unfired pellets. There is no noticeable shrinkage in the high-grade permanente mixture. This superior bond formation is achieved by the use of vaporized silica. The particles, as fine as in cigarette smoke, are tiny spheres when viewed through an electron microscope. The larger spheres on the right are coagulated globules of silica. The black portion at the left is only a fraction of a grain of magnesium oxide, ground to the fineness of ordinary talcum powder. It is these 2 fines, vaporized silica and minus 325 mesh magnesium oxide, that form the bonding mixture. The vaporized silica is so fine that a considerable quantity may be dissolved in the magnesium oxide without increasing the initial volume. Likewise, this mixture dissolves in the aggregates, making the compressed brick at its maximum density. Firing the closely compacted bond particles causes them to form the ceramic bond, magnesium orthosilicate, by a solid phase reaction. In a solid phase reaction, the materials react and crystallize in the new form without an intermediate liquid stage, as there is with average bonding materials. The ultrafine particles begin to react at a temperature as low as 1500 degrees and gain strength rapidly as the temperature is increased. Because no liquid forms, no sintering shrinkage takes place. Therefore, the volume and density of the refractory is not appreciably changed after firing. High density in refractories reduces their porosity. This brick, cut to expose its interior after it had been soaked in red dye, shows color absorbed by the pores faintly only at the edges. Compare it with another brick of greater porosity that shows color over halfway through. Just as the denser brick absorbs less color, it absorbs less destructive slag and furnace gases. Destructive chemicals react with or flux the brick material, causing them to lose their refractory structure. This microscopic thin section shows that geometric crystalline structure is still present in this permanente brick after more than a year's severe service in a glass furnace. A section from a test brick of average bond and density shows the ravages of destructive fluxing, the loss of refractory structure, conversion of crystal to liquid, which gradually loosens and flushes away the brick structure. This brick saw the same service as the permanente brick. Now that we have established a few of the requirements and characteristics of basic refractories, we shall see an example of how they are put to use. An open hearth furnace for making steel from pig iron or scrap is a refractory furnace that receives especially severe treatment. This open hearth is nearing completion after being rebuilt from top to bottom. The brick are laid up without mortar, held in place by their own weight and supported by an exterior steel skeleton. Inside, the back wall is just being completed. Some of the courses may have steel sheet or ground chrome or mud placed between them to help fuse the brick surfaces under firing. After the roof and walls are installed, the great hearth bottom is rammed in. A ramming mix, similar to a brick mix, is spread over the general contour of the furnace bottom, then compacted into one giant basin that will hold the molten steel. The ramming mix was blended in dry form at Permanente's refractory plant. It contains all the necessary ingredients, just as the brick mixes do. The dry mix is dumped into a common cement mixer, where it is stirred with a small proportion of water to aid in compacting the material and setting the chemical bond. When the proper amount of moisture has been added, it is emptied onto a conveyor belt and carried to the furnace. The process of building up a huge monolithic basin will continue until the desired thickness has been reached. The floor will be filled to the bottom of the tap hole seen in the back wall. The finished hearth, capable of holding 250 tons of boiling steel, is first warmed with gas flames to set the chemical bond. Then it will be burned in with the furnace burners gradually being raised to full firing temperature. Permanente basic refractories play essential roles in many modern industries, and their quality has great influence upon the production capacity of every furnace in which they are used. I was conceived in need and developed in research. I am produced through careful selection, control, and plant organization. The members of my family were evolved for specific uses and performed their duties well. My creators are ready, through Kaiser Research, to add to my family to serve your special needs as you may require. Progressive methods demand refractories that withstand heretofore unobtainable temperatures and volume of production. Permanente Pericles has been synthesized through intensive research by Kaiser Chemicals Division. This Pericles produces the finest refractories. During World War II, expanding Kaiser Industries needed improved refractories. Having a qualified research and engineering staff of long experience and their own proving grounds, they selected Natividad in the California Coast Range near Monterey Bay as a source of high magnesia lime. Here they built a mineral processing plant, a network of belts containing the lime mineral, Careful fracturing of the quarry face causes the material to descend as it is dug away. But occasionally a large piece must be reduced by mud capping. A charge of dynamite stuck to the surface with wet clay shattered. Reducing a mountain to a usable form is the first step in separating the high magnesia lime from unuseful materials occurring in natural deposits. Monstrous electric shovels dig away at the broken rock, placing it in dump buggies for transportation. Crushers and classifiers that finally beneficiates and activates the starting mineral in a number of great tubular rotary kilns. In spite of the 40,000 tons of cleaned mineral quarried each month to supply the plant, this mountain provides an inexhaustible resource of high purity minerals. This quarry yields high magnesia lime suited to a closely integrated plan of production. The essence of the plan? Careful selection of materials and rigid control of methods to produce highest quality refractories. My manufacture starts with everything falls from the crusher onto the endless belt that travels to the primary classifier. The screen mesh is designed to retain all of the pure mineral possible and to reject the more finely divided waste to the tailings pile. From the primary screen, the magnesia lime is carried down to the processing plant, where it is washed with high-pressure sprays to remove adhering waste. Every precaution is taken to deliver only the cleanest mineral of the quarry to the stockpile. The rock then takes a scenic railway ride up a 100-foot boom and plunges to the pile below. The mixture of mineral and waste is dumped into a large hopper from whose mouth the rock is slowly worked by the grizzly so that it is fed continuously into the maw of the primary crusher. Converging steel plates working against each other crush the rock into smaller pieces. This is the first phase of purification. Another unusual feature of this quarry is the discrete structure of the mineral. The jaws crush, the rock cracks along the weak veins of included impurities, and the residue crumbles from the chunks of pure magnesia lime.